Good morning, everyone. Uh, Welcome to session 11, Unit 2, Engineering Mechanics and Strength of Materials. In the last class, we are discussing about temperature stresses. Every material is subjected to a change in temperature and it undergo change in dimensions. These dimensions are restricted to deform, then it is subjected to stresses. Then it is subjected to stresses. For that, what is the effect of temperature on the bar or an element or in structure? We need to find out. So that is with the help of thermal coefficient of expansion alpha for different materials which we are going to use. Okay. In this class, we are going to discuss about types of load acting and strain energy and the problems on that. Okay, so let's start with our today's session. Types of load acting. The first type of load which is acting is gradually applied load. What type of load it is? Gradually applied load. For example, we need to place a number of books on a table. We are not keeping the books on the table at a time. We are keeping one books over the other books. We are following the same till the completion of keeping all the books on the table. This is the way gradually we are increasing the load on the table. Gradually we are increasing the load on the table. Okay, because it is a cumulative after that completion of that all the books. This type of loading which is called as gradually applied load. Gradually applied load. Okay. For example, one more example is given here. When a load is applied in a installment, that is the load of 100 Newton to be applied. The first a load of 5 Newton, then 10, then 15, then 20 Newton, and we are going to continue till 100 Newton is applied. Overall, it causes less stress and less strain as compared to suddenly applied load. For the same loading, we are applying 100 Newton at a time, then it will be more stress and more strain. More stress and more strain. So this is what gradually applied load. This is what gradually applied load. Okay. Here the pictorial representation is given. See, there are a number of box packs they are keeping onto the truck. They are loading onto the truck. See how they are loading one rack over the other rack after other rack. See how the loading is going to be applied. This type of loading is called as what? Gradually applied load. The most gradual applied load is found during testing of materials in universal testing mission. In what type of machine? It is a universal testing machine. There is a first tension test of a steel bars and all, or compression test of the concrete blocks. We are increasing in order by order. We are installment by increasing. This type of loading is called as what? Gradually applied load. This type of loading is called as what? Gradually applied load. Understand? And how that the gradually applied load? See again, placing of 20 books one by one on a table and the above the other. This is also an example of gradually applied load. Gradually applied load. Okay, next, the stress is equal to P by A, and here we can give the graphical representation when the load is applied P and the change in length delta L deformation, and this load under the curve how it is behave. This is called as strain energy, and this is called as strain energy because we are keeping one over the other. We are keeping one over the other. We are keeping one over. So that's why this type of loading which has not much impact, not much impact, and it will not cause much stress as well as strain. Okay. Next type of loading is next type of loading is suddenly applied load. Suddenly applied load. See the name suddenly applied. It indicates that see how it is applying over the testing of soil. Testing of soil. We are allowing the impact load from a height to a trolley. Okay, we are allowing a impact load something weighing some block which is dropping from certain height. This is how it will impact on the ground. This is how it will impact on the ground. Okay, in the same way here also they are keeping the number of layers of box or one or the other and dropping suddenly. This is what suddenly applied. Okay, when total force is applied in one installment, that is force of 100 Newton is applied in one installment, it causes two times the stresses as compared to when the load is applied gradually. Double stress ಎಷ್ಟಾಗುತ್ತೆ double. So that's why this is having much what stresses on the ground or where we are applying that suddenly applied load. Okay. Example, weight of 50 kg is placing in a weighing balance. ಒಂದೇ ಸಲ ನಾವು ಇಟ್ಬಿಡೋದು ಯಾವ್ದ್ರ ಮೇಲೆ ಬ್ಯಾಲೆನ್ಸ್ ಮೇಲೆ. ಅವಾಗ ಏನಾಗುತ್ತೆ, the strain on the machine will be more and stress on the machine will be more. Okay. Next, placing television on a table. ಅದು ಒಂದೇ ಸಲ ಇಡಕ್ಕೆ ಸಾಧ್ಯ ಟೇಬಲ್ ಮೇಲೆ ಟೆಲಿವಿಷನ್. ಸೊ ಹಂಗಾಗಿ ಅದು ಯಾವ ಟೈಪ್ ಆಫ್ ಲೋಡ್ ಆಗುತ್ತೆ, ಸಡನ್ಲಿ ಅಪ್ಲೈಡ್ ಲೋಡ್. We cannot keep the spare parts as one by one. It is assembled one, we need to keep it one at a time. So that is also suddenly applied load. Next, placing a bundle of books on a table. So 20 books is there, we are keeping it on time. That is what is called as suddenly applied load. Suddenly applied load. And this suddenly applied line causes two times stresses as compared to gradually applied load. Gradually applied load. Gradually applied load. Okay. So this is how the stress pattern for the gradually suddenly applied load. See, sudden we are instant stress strain curve. It is shows the rectangular pattern or are equal in nature. Okay, so this is what strain. This is what strain occurs. Okay, understand. Next, impact load. See, first one. So for that reason only I am keeping the diagram. See what type of loading it is. Impact. How it is dropping. See, you can see that how it is dropping from a certain height to a collar. Here a fixed support attached to a bar with a collar, and collar is released suddenly and it is dropping over the bar which is attached with this. Then what happens? It is an impact. It is an impact. The bar of length L, the load of P which is applied as an impact load, and change in deformation is delta L. Change in deformation is delta L, and it is dropping at a certain height H. Dropping at a certain height H. Okay. See, impact load is a moving load. The moving body striking another body. The moving body striking another body creates impact load. Best example is accident, bus accident, and suddenly the car will hit the trees, hit the culvert, hit the bridges, whatever that is. It is what is called impact load. Impact load. It causes many times stresses when if some load is applied gradually. Example, force applied in an accident is an impact. Force applied in what? Accident is an impact load. Okay, hammering is another example for impact load. We are going to hammer when we are making the tools according to our requirement. That is also what impact load. Okay, next, striking ball with the bat is a impact load. When we are facing the ball from another end, bowler is bowling, then we are hitting the ball. That is also called as impact load. Okay, next, jumping on the chair. Jumping on the chair causes impact load. So we are jumping from mm, ground to the chair. That is what is called as impact load. Next, falling of an object from the hand and striking the foot. It is an impact load. Many times it happens to us. Many times it has happened to us. We are holding some materials in our hand, and due to maybe some reason it is fall on our foot. That is causes impact load. This causes impact load. Okay, and that equation is given by, then that equation is given by, what is this is, F is equal to stress is equal to W by A of 1 plus square root of 1 plus 2 HAE divided by WL, divided by what, WL. This is what impact. This is what impact load. We cannot assess how the effect will be. Many times it causes stresses as compared to gradually applied load. Gradually applied load. Okay. Next, one more thing. The word strain energy we need to use. Where we are going to use strain energy? When we apply a load, it is undergoes deformation. That causes a strain in material. That causes a strain in material. So due to that, after removal of loading, the strain will be released. Strain will be released. See, the spring is subjected to a load. It is compressed. After removal of loading, it is expanded to a original position. Again, see, strained, released. It is strained and released. Once strained, the amount of energy stored due to strain, it is called as a strain energy, and which is in elastic limit, okay, because after removal of loading it will comes to original shape. The energy will be released again. Energy will be released again, right? Energy will be released. For example, we are having some uh, some material to taking place some other place. Our hand which is holding, it will also for a little time it will be strained. Then after keeping the material over a place, then what happens, we will going to release the strains through our hands. So this is what strain energy. Why it is so important? It is important, much important, because we need to load the material up to its elastic limits in order to keep the material safe conditions. Otherwise, what happens? That strain is permanent, and energy stored is permanent. It is no more use. It is no more use. So that's why we need to load up to an elastic limit. Here, it is an elastic limit. The energy stored to loading, the strain energy is called as what? The energy stored due to straining of material, and it will comes to its original shape after removal of loading. After removal of loading, that is what is called as strain energy, or it is also called as resilience. Or it is also called as resilience. So it is if a material is strained by a gradually applied load, you keep in mind. It is not suddenly load or impact load. Is what type of load? It is a gradually applied load. Then work done on the material by the applied load. When the work done, it is stored some energy. That's work done is called as. strain energy. The work is stored in the material in the form of what? Strain energy. If the strain is within the elastic range of the material, this energy is not retained by the material upon the removal of load. After removal of load, what happens? If it is in elastic limit, it comes to original shape and size. Okay. Next. Here we have how the strain energy stored with the help of a graph. We can explain this. See how it is loading here. Figure below shows the load extension graph of uniform bar. Okay, the extension and the change in length is on the x-axis and load applied on y-axis, which is within the elastic limit. The shaded area represents the work done in increasing the load from 0 to its value. It is 0 to its value. It represents what? Work done. Okay. So work done is equal to strain energy of the bar, or it is shaded area, and it is strain energy is equal to P into delta L by 2 for a gradually applied load. You remember this into volume. Next, strain energy is equal to same stress into strain divided by 2 into volume. Same way, strain energy is equal to F square by 2E into volume. And it is unit of strain energy. It is what? Say joules is expressed in work, and it is joules or Newton per meter. Newton per meter. Okay. Newton per meter. Next, the strain energy modulus of resilience. So, strain energy is also called as resilience. Is also called as resilience. So, I wanted to use some more extra point here with respect to strain energy. What is that? If we are loading maximum up to which it can hold the strains and it is in elastic limit. So that kind of load which is applied and the strain energy stored is called as proof resilience. Proof resilience. Proof resilience. What is that? Maximum strain which can be stored in a body when the load is within the elastic limit is known as proof resilience. So beyond that it cannot hold that. Beyond that it cannot hold that. What happens? It's called as permanent deformation. What is that? Permanent deformation. So up to that, the maximum strain which can be stored and the loading condition is within the elastic range. That is called as proof resilience. Okay. Modulus of resilience is nothing but strain energy per unit volume. Our proof resilience per unit volume is called as what? Modulus of resilience, and it is given by F square by 2E into volume. Square by 2E into volume. Okay, where F is the stress and E is the Young's modulus. Square is stress and E is the Young's modulus. Understand? Okay, now the how the resilience which is will going to be move according to the applied load, and which is an elastic limit. The loading of the material will show the graphical representation. See here, it is the stress and here is the strain, and the load applied gradually. It moves elastically up to limit, and the stress is proportional to strain, and the behavior is linear behavior, and then it heals, and then it changes the curvature of the what stress strain distribution curve. It starts after yield point, and it will be safe up to what ultimate strain, but the from yield point to ultimate strain the deformation is permanent. Again you should remember, it will only be releases of load will comes to its original shape up to what point? Up to what point? This stress modulus of resilience, when the stress is proportional to strain. It is called as elastic point. Up to the elastic point, up to the yield point. So the material will regains its shapes or deformation is disappear. So for that, we need to understand what's the importance of property of elasticity of material when we are loading, based on that, we need to assess the strength of the material. We need to assess the strength of that area material. Okay, see the area under this linear relations is triangular in shape. Triangular in shape. This is called as modulus of resilience. And the maximum load which can be carried it is called as ultimate strength. Even still the material will not be felt. It will be strained. It will be strained. It will be strained, and it is comes to fracture at some point of loading. Even the loading value is decreased after ultimate load. Till the ultimate loading will be get increased, stress will be increased. After ultimate load, stress value decreased, but material won't stand alone. It will be get failed. So this is called as modulus of toughness, and so Young's modulus is stress by strain. Here you can see the beautifully how the modulus of resilience will be occur in this. So this area into breadth is called as area into thickness or breadth, which is gives the what length, which gives the volume. So strain energy per unit volume, which gives modulus of resilience. Modulus of resilience. Understand? Okay. Next, we move on to types of loading. The comparisons of three types of loading. This is gradually applied load, suddenly applied load, and impact. And what? Impact load. The gradually applied load is nothing but we are loading in the installment. Suddenly applied mode, it is a instantaneous. It is a instantaneous or instantly applied. And impact load is it's a fall from certain height or dropping certain material from a certain height. Okay, that is what impact load. And with respect to this, we can assess this stress is P by A for gradually applied load, and for a suddenly applied load, it's two times the stress of the gradually applied load. For impact load, you cannot assess directly. So, what exactly the stresses will develop due to impact loading? We need to find that by using so many parameters. See the load divided by area plus this is first. Okay, then again square root of load divided by area whole square plus 2e wh divided by al. This is what the difference of three types of loading system. Three types of loading system. Understand? Okay. Let's move on to next. Should we solve some problems? Okay. Numericals. Okay. Problem. I will read out the problem. Calculate the strain energy stored in a bar of 2 meter length, 50 mm wide and 40 mm thick, when it is subjected to a tensile load of 100 kN. Subjected to a what? Tensile load of how much? 100 kilonewton. See, subjected to a load of how much it is? 100 kilonewton. Correct. So that is a meter. It is given. I will change it in it. The width is 40 mm. It is how much? 40 mm. When it is subjected to a tensile load of how much? 100 kilonewton. Draw the free body diagram. It is how much? 2 meter length. Correct. 2 meter length, and it is 50 mm wide and 40 mm thickness, and it is loaded how much? 100 kilonewton. Tensile load. Tensile load. What should be the strain energy if you are loading by 100 kilonewton? Write the given data, and E is given for this problem 2 into 10 to the power of 5. It is a steel bar, of course. Newton per mm square. 2 into 10 to the power of 5 Newton per mm square. L is 2000 mm because it is 2 meter. We are keeping all units in Newton millimeter, and B is 50 mm and T is 40 mm and P is 100 kilonewton. Okay, next, now find the area B into T. 40 into 50 2000 mm square. Okay, volume A into L 2000 into 2000. We find out that keep in mm cube, and stress is equal to what? P by A. Correct. Stress is equal to P by A. P is 100 kilonewton. So that find out that next strain energy F square by 2E into volume. See, So this is what the strain energy value. Okay, this is what the strain energy value. Okay, what you need to find out, you should remember the formula, substitute and up the using calculator you should calculate properly, then you will get the right answer for this. Strain energy is equal to F square by 2 into volume, stress is equal to P by A. Okay, this is what the problem is. This is what the problem is. Okay, first of all, what you have to draw here, see, when they have given the problem, you should read properly once or twice, then you draw the free body diagram, you will understand. Okay, then you write the given data and what you need to find out here. Only strain energy they are directly asking, only single question. So move on to next. Then substitute for the stress, because FV1, then you substitute. E is given, volume you can find out by material property, then substitute all and calculate and place the final answer. Final answer. Okay. Next, problems on load applied suddenly. Okay. I will read out the question. An axial pull of 50,000 Newton is suddenly applied to a steel rod of 2 meter long and 100 mm square in cross section area. Calculate the strain energy that can be stored when E is equal to 2 into 10 to the power of 5 Newton per mm square. 2 into 10 to the power of 5 Newton per mm square. Okay, draw the diagram and write the given data. P 50 kilonewton or 50,000 Newton, L is equal to 2 meter, A is equal to 100 mm square is directly given. E is a steel bar 2 into 10 to the power of 5 Newton per mm square. We need to find out Q. Write the diagram for this. See, 2 meter length, correct? 50,000 Newton is applied, correct? And volume we can find out area into length. And stress, it is suddenly applied load 2 times the normal stress. Okay, P by A. You can find out this. Next, strain energy F square by 2E into volume. F square by 2E into volume. Substitute all and you will get the answer. Okay, this is how we can solve this problem. See, if nothing is specified, the previous problem what we did, see, here it is F square by 2 into volume, correct? Stress we are finding P by A, because here nothing is specified about whether it is gradual load or suddenly applied load, right? We are assumed it as a gradual loading. Correct? Okay, here in this problem they have given it is load applied is suddenly, so that's why what we are doing is, in order to find the stress, we are using, see, we are using what? C stress is equal to 2 into P by A. 2 into P by A. Then we are finding strain energy by using same formula, F square by 2 into volume. F square by 2 into volume. Okay. Next, one more problem. I will read out the question. An axial pull of 6,000 Newton is suddenly applied to a steel rod of 4 meter long and 50 mm in diameter. Calculate the strain energy stored when E is equal to 2 into 10 to the power of 5 Newton per mm square. Okay, write the given data. P is 6,000 Newton, L is 4 meter, D is 50 mm, and E is 2 into 10 to the power of 5 Newton per mm square. What is the value of strain energy? Okay, write the diagram for this. 4 meter long, 6,000 Newton. Okay, area pi d square by 4 is 3.14 into 50 square divided by 4. Okay, right? Next, volume, area into length 4 meter, which will use the volume, right? Then you have to find out stress 2p by a. Why 2? It is suddenly applied load. 2 into 6,000 divided by area, which is 611.62 Newton per mm square. Okay. Next, strain energy is equal to F square divided by 2E into volume. I will change this unit. It is the slight formula I have to change here. Okay, F by 2E into volume, right?